All right, let's journey out into the cosmos to check out a truly beautiful marvel, the star cluster Messier 11, which also has the much cooler name, the Wild Duck Cluster. And it's a good thing we're visiting because hidden deep inside is this strange, rhythmic secret that we're going to uncover together. You see, when we look really, really closely at this cluster, we find that some of its stars aren't just shining steadily. Nope, they're actually pulsating, almost like they have a heartbeat. So the big question for us today is, what is making them tick?
To figure this out, we first need to get the lay of the land. I want you to think of Messier 11 as this huge, bustling city of stars. It's pretty much the perfect cosmic laboratory, because it's just packed with thousands of stars that were all born around the same time. This gives us this incredible snapshot of a star's life cycle. So M11 is what we call an open cluster, and you can find it in the constellation Scutum, the Shield. It's about 6,120 light-years away, so not exactly next door. But what's really crucial for our investigation is its age. It's in this perfect intermediate sweet spot. Not so young that it's still all messy and shrouded in gas, but not so old that its most interesting massive stars have already fizzled out. It's just right.
But like I said, something's a little off in this stellar metropolis. When astronomers were studying M11, they noticed that some of its story residents just aren't constant. They flicker. Their brightness goes up and down over time. And it turns out these little oddities, well, they're the key to our entire mystery. So let's dive into these flickering inhabitants. In the biz, astronomers call them variable stars. And to solve the puzzle of this cluster's heartbeat, we've got to first understand what could make a star's light change in the first place. Okay, so what is a variable star? The definition is actually super simple. It's just a star whose brightness seems to change over time when we look at it from Earth. But the reasons for that change, well, that's where things get really fascinating. And it usually boils down to two main culprits. On the one hand, you've got the most straightforward cause, eclipsing binaries. This is when what looks like one star is actually two, circling each other. And when one passes in front of the other, from our point of view, the total light we see takes a little dip. It's really just a trick of geometry. But on the other hand, we have what we're really after today. Intrinsic variables. These are single stars that are genuinely changing all on their own. The actual physics inside the star is causing it to get brighter and dimmer.
So let's zoom in on these intrinsic variables, these incredible single stars that are physically pulsating. They're not just flickering, they're literally growing and shrinking. You could say they're breathing. And in M11, they belong to a very specific class of star, the Delta Scuti stars. And, here's a fun little piece of cosmic trivia for you. This type of star is named after, you guessed it, Delta Scuti, a bright star in the constellation Scutum. That is the exact same constellation where our cluster, M11, lives. So it's really no surprise we find a whole bunch of them here. The real question is, where exactly in this star city are they hiding? To find our suspects, astronomers use something called a color magnitude diagram. Just think of it as a crime scene board for stars. It plots every star's brightness against its color, which tells us its temperature. Now, most stars spend their lives on this big diagonal line called the main sequence. It's like the main highway of stellar life. And our suspects, the Delta Scuti stars? They're not just scattered everywhere. Nope. They're all clustered together in one very specific area, right at the point where stars of a certain age are just beginning to evolve off of that main highway. Okay, so we found our suspects, and we know exactly where they hang out. But this brings us right to the heart of the investigation. What is the physical engine deep inside these stars that's driving this incredible rhythmic pulsation? What is actually making them breathe? The answer, and it has a fantastic name, is the Kappa-mechanism. This is the physics engine we've been hunting for, and it's this absolutely fascinating process that only happens under very specific conditions inside very specific stars, turning them into these amazing cosmic oscillators. To get this, we just need one key term, stellar opacity. It's represented by the Greek letter kappa. And all opacity means is how hard is it for light and heat to travel through the star's gas? If the opacity is high, the star is like a really thick blanket, trapping all that heat inside. If it's low, heat escapes super easily. Simple as that. And here is the paradox that drives this whole thing. Normally, when you heat up a gas, it gets more transparent. Its opacity goes down. For a star, this works like a safety valve. If a layer gets too hot, energy escapes more easily and it cools back down. No big deal. But in a very specific layer inside a delta Scuti star, where helium is being ionized, something totally bizarre happens. As that layer gets hotter, it actually gets more opaque. The safety valve doesn't just fail, it does the opposite of what it should. So let's walk through this cycle. Imagine you're too hot in bed at night, but instead of throwing the blankets off, you pull more blankets on? That's what the star does. First, heat gets trapped in that special helium layer. As it gets hotter, its opacity goes up. That's like pulling on another blanket, so it traps even more heat. The pressure builds and builds until it physically shoves the star's outer layers outward, making the star expand and get brighter. But as it expands, those layers cool down. And that cooling finally causes the opacity to drop. All that trapped energy rushes out, and the star shrinks back down, ready to start the whole wild cycle over again. It's a self-sustaining stellar heartbeat. So there we have it. We've solved the mystery of the stellar heartbeat. But so what? Why does this actually matter? Well, this isn't just some fun piece of physics. The answer tells us something truly profound about the entire star cluster. See, this whole Kappa-mechanism thing only works for stars of a very specific mass, at a very specific point in their lives, right as they're about to leave that main sequence. So finding them there isn't an accident. Their very presence acts as a precise cosmic clock, telling us the age of the entire cluster. And by using these pulsating stars as a timer, astronomers can pin down the age of Messier 11 with incredible precision. The wild duck cluster is 222 million years old. Here's the bottom line. That flickering we started with isn't some random quirk. The fact that these pulsating delta Scuti stars exist in exactly that phase of their life is the living proof of the cluster's age. The heartbeat we set out to find is also the ticking of M11's very own cosmic clock. And that really makes you wonder, doesn't it? Every single one of these beautiful star clusters is its own unique laboratory, basically frozen at a specific moment in cosmic time. If a simple stellar pulse can tell us all of this, what other amazing secrets are just waiting for us to uncover in the next star city we decide to explore?